Hello guys, and welcome back to Engineering Hack, where we're trying to solve engineering problems in a way that's hopefully easy to understand. Today we're doing a very basic problem on the idea of thermodynamics, but really it's very in the beginning because we're looking at pure substance analysis. So this is a 101 question on how to find properties for different pure substances. In this case, we're dealing with water. So this is, the super basic skill you need to be able to then later on solve problems for refrigerants, for refrigerators, for air conditioners, for motors, diesel motors, ice motors. So this is, the basic skill you need to have. So we're going to solve this problem. This is one of those problems that, we're going to solve it. You're going to see the step-by-step of how to do it, but you need to be very comfortable doing this. So go back, do it yourself, ensure you get the gist of it, all right? So this question is from UNSW, and it reads like so. Determine the values of enthalpy H, specific volume V, and the quality X of 1 kilogram of water containing a closed system under the following conditions. A. Saturated liquid at 500 kilopascals. B. Saturated vapor at 1 megapascal. C. Wet steam of quality 0.8 and 300 kilopascals. D. 200 kilopascals and 60 degrees Celsius. And E. 500 kilopascals and 200 degrees Celsius. Okay, so note that this is 1 kilogram of water. Note that this is a closed system, so there's no mass entering or leaving. There's no problem in regards to any changes. It's super simple, very straight to the point. We need to determine the enthalpy, right? And you don't need to know this, but remember that enthalpy is the convenience property that relates the internal energy and PV. You don't need to know this for the problem, but just to remind you. Specific volume that we are going to use the fancy V, like so, right? So the Greek one. And specific volume is just defined as the volume divided by the mass, okay? So it's inverse of the density. And last but not least, the quality. And the quality is probably the one that's least familiar if you're first starting this, but the quality is defined as the mass of vapor divided by the total mass, right? So what is the total mass? Total mass is the amount of liquid you have plus the amount of vapor. So the quality is a ratio, it's a percentage of how much vapor you have in terms of mass in respect to the total. Okay, so if you have only vapor, it's going to be 100%. If you only have a liquid, it's going to be 0%. So let's get started. We're looking at 1 kilogram of water. It's saturated liquid, right? So they're giving us already valuable information, saturated liquid. That already tells us about the quality, right? As there's no vapor, so therefore quality is 0 at 500 kilopascals. So for part A, we can start saying, okay, so for part A, the quality X is 0, right? Or 0 or 0%, doesn't matter, same thing. Okay, why? Because saturated liquid by definition is a point in which you have no vapor whatsoever. If you give any amount of energy to this kilogram of water, it will start to form vapor. But until then, it's only liquid. So therefore, the quality is 0. And then to find the enthalpy in a specific volume, I need to use property tables, right? So I have two property tables here with me. I have the one from UNIS and I have the one from Rogers, okay? Depending on what you do, we're going to use different property tables. They're all very similar in structure. There are slight differences. I find this one to be very way easier to grab properties for. If you're students, you don't have to go back and forth as much. But let's do a couple of them with both tables so you get familiar with both, okay? So let's start with the Rogers one. I'm going to go into the saturated water and steam table. I'm going to look for, where are we? Saturated water. And I'm looking for the pressure table, right? So this is really giving me the information in temperature, and I'm really looking for the information in pressure. So here you can see that we just went from temperature into pressure, okay? And here I'm looking for the 500 kilopascals. Note that this is in bar, so we have to do the conversion. It's going to be the 5. So you go back down here. You look for the pressure. 5, and here you go. 5 bar, equivalent to 500 kilopascals. And here's where you're going to get the information that you need. So in our case, we're looking for enthalpy and specific volume. And this is the value for enthalpy in this state that I'm in, right? It's going to be about 640 kilojoules per kilogram. So this is the enthalpy for the saturated liquid. This is the enthalpy for the saturated vapor. And this is a difference between the two. Okay, that can be useful depending on the calculation you're doing. So because I have a saturated liquid, then this is the enthalpy I'm looking for. So the answer there is 640 kilojoules per kilogram. Specific volume, we can read it off here, meters cubed per kilogram, volume over mass. And the one that I'm looking for is going to be the 0.3. However, okay, and this is a very easy thing to get wrong. This, it's hard to see, but there's a G there, right? This is a G. So we're looking at this symbol here. So this is a specific volume for the saturated vapor. Okay, and as we know, we don't have the saturated vapor, but rather the saturated liquid. So what we're reading here off this table is incorrect, because this is the specific volume if we were to have saturated vapor. We don't. We have saturated liquid. So this is no good for us. We need to go to a different table, and this is where I say that Rogers, is a bit more painful to work than the other tables, because then we can't use this table here. We need to go into a table that relates the, where is it? Superheated, further properties. And here we're going to have, again, tough to see, but this is F. So this is the property for the saturated liquid. And then here I'm going to have to look for the right pressure. So I need to find 5 here. And then I don't have 5. So I'm going to have to interpolate between these two numbers, because the number that I'm looking for is going to be between these two numbers. So a lot of traps that you can fall, right? The specific volume for my case here of 500 kilopascals saturated liquid is going to be between the 0.1 and the 0.11. And the last trap that you don't want to fall into is, if you know, let me just do this. If you zoom on the other point here, you're going to see that this is 10 to the minus 2. Okay, so it's not 0.10191, it's actually 0.001091. So then interpolation there to get the 5 to the 5 here, and then you get the value here. Now I'm going to show you this on the other table. All right, this is by, again, the units table here, and I'm going to go into the saturated water table. Where are we? Here, saturated water table, and this is the temperature table. Not interested because I have pressure, not temperature, so I'm going to go down and now go into the pressure table. This is the one I'm looking for. I'm looking for 500 kilopascals. It's already in kilopascals, so that's great. And here's 500. And all in one table, I have the internal energy that I was looking for before. Enthalpy, right? No, enthalpy. The enthalpy I was looking for before, and remember it was 640. So this should also be 640, and there you go, it is. There's a slight difference in the actual number from one table to the next. And then the specific volume, I have both the vapor and the liquid. So I don't have to use two different tables. They're all in the same table. So I can go ahead and indeed see that this is 0.001093. Okay, so it simplifies my life a bit. I don't have to interpolate. I don't need to watch out for that 10 to the minus 2 there, and I don't need to use a second table. And I don't have to convert bar in kilopascal. So, I find this to be easier. But at least for the next example, let's look also on Rogers, just to be sure we're comfortable with both. So that's our answer there. Where are we? Here. Okay, so for part A, our answer is that quality is 0, that my enthalpy is 640 kilojoules per kilogram. And I'm going to go ahead and say approximately, because we saw that there's the other variation on the other one. And then specific volume for my case 1 is 0.001093 meters cubed per kilogram. So that's our answer right there. Okay? So let's move on to B. Okay? So now B, we have saturated vapor, not water, so not liquid, saturated vapor at 1 megapascal. Okay, so now we're looking for the G1, so VG, HG, and so on and so forth. Okay, you think that this stands for gas if you want, as a easy way to remind yourself. So let's go down. We're going to go the same thing. Okay, saturated water, steam tables. This is the temperature one. I'm not interested in this one because I have a value for pressure. Here's my pressure. At 1 megapascal, so that's going to be 10 bar right here. So this is the line I'm interested in. I am looking for the enthalpy, so saturated vapor enthalpy. So this is the enthalpy of this state, 2778. And for my specific volume, this is exactly what I'm looking for, right? So, and there's no 10 to the minus 2, right? So watch out for that. This case is exactly what you're reading, and we read it off here, and the specific volume for our case is 0.1944 meters cubed per kilogram. So we can take note of those. Those are going to be our answers, all right? Now let's go to the other one. Same thing. Answer should be very similar, obviously. Pressure table, we're looking for 1,000 megapascals is 1,000 kilopascals. So here we are at 1,000 kilopascals. Oops, 1,000 kilopascals. Boom. I'm looking for enthalpy for the saturated vapor. So saturated vapor enthalpy right there, 27777.1 or 2777.1, right? So very similar to the one we just read on the writer's table, and obviously saturated vapor on a specific volume, 0.19436. Okay, so those are going to be our answers right there. Where's our B? Here we are. Okay, so quality. What's the quality when I have a saturated vapor? Well, 100%, 1 or 100%, right? 1 or same thing as 100%. Why? Because I have no liquid whatsoever. That's the definition of a saturated vapor. What is the enthalpy that we found for case B? The enthalpy was 2777 point, what was that we found? Point something, 0.1? I think it was 0.1. And that was in kilojoules per kilogram. And then the specific volume we found to be 0.19436 meters cubed per kilograms. Okay, so that's it for our part B. Let's go on to part C, in which we have wet steam of quality 0.8 and 300 kilopascals. So now we have a quality, right? We're given a quality. So if we have a quality of 0.8, we obviously automatically know the quality. That's, that's the obvious part of it. So that's 0.8 or 80%, same thing, right? Or 80%. And that automatically tells us, well, we have part of this mixture is vapor, part is liquid. Specifically, 80% of this mass is vapor and the rest of it is liquid. So if I want to find out the properties, any thermodynamic properties, what I need to do is account for the properties of both the liquid and the vapor. Okay, so I'm going to go into this table now. What was the pressure? 300. All right, so I'm going to go here. Again, I don't want the temperature table, I want the pressure table. I want to look at 300. So 300 falls right here. Right here, 300. Let me eliminate the ones from the previous one. And I am interested in the specific volumes and the enthalpies. Okay, how does this work? Well, if I have 80% of vapor and 20% of liquid, therefore I have 20% of this and 80% of this. So I'm multiplying 80 by this and summing with 20% of this. All right, I'm doing a weighted average, I guess, yeah, of sorts. Okay, and that's how I'm going to find both properties. Both properties. Okay, so 20% of this and 80% of this. It's as simple as that. Okay, so what the math becomes is I'm going to do, let's do it here in the corner. The specific volume for part C that we're looking for will be 20% or 0.2 of the 0.0013 or 1073 plus 0.8, the 80% of the vapor, which is 0.60582. By the way, whenever you're doing these, okay, always remember that vapor occupies more volume than liquid, or gas occupies more volume than liquid. So therefore, if when you're doing this, you can always check out this number should be way greater than this one every single time. if you flip it, obviously you're going to get a wrong answer, but it's an easy thing for you to check as you're doing your math, if this makes sense, right? Okay, and then the result of this is that the mixture that I get here is 0.4848, and then the answer is on the same unit as both these guys, because these are a ratio and therefore dimensionless. All right, so that's our specific volume. And then for the enthalpy, exactly the same thing, exactly the same deal. All right, if I want to calculate the enthalpy, let's do it here, bottom here. If I want to calculate the enthalpy of part C of our problem, all I need to do is point to, actually, you know what I'm going to do? I'm just going to go ahead and copy this to stress that it's the same thing. It's the same exact idea. But then instead of putting the specific volume here, I'm going to put the values for the enthalpy. So this is 561.43, and this here is 2724.9. All right, and then I do this math, and after this math I get it 2292.2 kilojoules per kilograms, same units as the enthalpies, individual enthalpies, right? Again, same thing, okay, same idea. When you're doing these, the vapor always will have more energy than the liquid, always, right? And it's significantly more. So you can always check for that to see if it makes sense. Oh, by the way, you can also check if your answer makes sense, your final result coming out of your calculator, because, you look at, we have 80% of this guy and 20% of this guy. So therefore, the answer should be way closer to this than to this, right? The mixture should be way closer to the 2700 as opposed to the 500. And indeed, right, we get 2200. It's way closer. And that's another way that you can check your math as you're doing this. Okay, so these are the two. Let me grab these. I'm going to put up there with the other answers. Here we go. So enthalpy turns out to be 2292.2, and that's kilojoules per kilograms. And vapor turns out to be 0.4848, and that's meters cubed per kilogram. All right, so let me go ahead and eliminate this, and we can move on to the next one.